Hey, welcome back. Second Kinematics video. So some of you, this will be your first time watching at home because you were in person on Tuesday. And some of you, this is your second time watching at home. But either way, it's going to be a really good video. If you're thinking, hey, wasn't Mr. Dooley wearing that shirt in the last video? Yes, I was, because actually it's still before school starts and I'm just trying to get ahead of you a little bit. So I'm making several videos. But just to mix it up, for this one, I think I'm going to use the green marker, where last time I used the blue. So we are looking at the same sheet again. I told you this was an important sheet. So I'm going to be going through some of these terms again and trying to maybe get them in your brain a little better than I did last time. And then we'll be doing some more work with picking the right equation so that you just get really comfortable with this. So last time I mentioned that there's these things called scalars, and then there are some things called vectors. Okay? And a scalar, I said, is just a magnitude. We don't care about the direction. So an example of that would be distance. All right? Whereas a vector, we do care about the direction, and so I said an example would be displacement. So distance is just total length. And displacement is the distance and direction from the start. From the origin. So let's just say that that green line right there is going to represent our origin. Right? And we've got a couple kids here, and they both take off from the origin. And Ned is going to go out we'll say out 10 meters and then come back 5 meters, where Paul is going to just go out 7 meters. I don't know if I made those to scale right or not, but this will kind of give us an example. Okay, so if we wanted to talk about their distance, Ned went a greater distance, right? Because total length traveled for Ned is 15 meters, so that's more than Paul. Paul's distance is only 7 meters. But if we're talking about displacement, Ned's displacement is only 5. Right? You could say it's like 5 east or 5 to the right, because he ended up 5 to the right of where he started. Positive 5 would be another way to include the direction. Okay, we do need a direction when we talk about displacement, so positive 5 would be fine. Paul's is positive 7, so that's more. Okay, so why am I belaboring this? Because speed is distance over time. Speed is also a scalar because it's distance over time, where velocity is a vector because it's displacement over time. Right? So let's say that this took them 1 second to accomplish this. Well, Paul's velocity is 7 meters per second because he went 7 meters in 1 second. Ned's velocity is 5 meters per second because he only went 5 meters in 1 second. So their velocities are different, and Paul actually has a bigger velocity because he's accomplishing more in terms of the vector that is velocity. If we're talking about speed, Ned went 15 meters in a second, which is too fast for humans, by the way, but he did it. So he has a greater speed. Paul's speed is just 7. Notice that Paul's speed is the same as his velocity. That's because he never turned around. So if you don't turn around, if you don't change direction at all, then you can use speed and velocity as the same thing, because they're both a rate of length over time, right? It's just that velocity includes the direction. So if there's no change in direction, you can use these as the same. Okay, that's important because we have one equation for constant velocity, and it's also the equation for speed. It's just v equals d over t, right? But I know that this d means displacement if I'm talking velocity, and it means distance if I'm talking speed. Okay, since velocity is a vector, acceleration also lives in this vector camp because that is the rate of change. Sometimes use the triangle for change in velocity. It's change in velocity over time. So anything that's built on a vector is a vector. In other words, velocity is a vector because displacement's in the formula and displacement's a vector. Acceleration's a vector because velocity is in the formula and velocity is a vector. So you're kind of starting to see which camp these things go in, whether we care about the direction or not. Right? The next thing that I wanted to emphasize today is that average velocity or average speed, for that matter, is not the average of speeds, right? It's total distance or total displacement over time. Average velocity is total displacement over time. And average speed is total distance over time. Okay, but it's not the average of speeds. So let's see if we can drive that point home. So let's say that you live here, and you're going to drive to Grandma's house, which is over here. And so you get in your car. It's the first car I've got to draw this year. Turned out pretty good. And we're going to go, so we start heading towards Grandma's house. Here, let's draw Grandma. I think that's important. And let's say that we go 60 miles per hour. Ooh, he's not using the metric system today. That's because Grandma lives in America. And we do that, and let's say that we do it for 2 hours. Grandma lives 2 hours away. We drive a constant speed or a constant velocity to Grandma's house. And then, just when we get there, we realize that we forgot something. Right? So we drive back home, and we drive back home at 120 miles per hour. Ooh, that's dangerous. And it takes us, how long do you think? 1 hour. If you figured that out in your head, by the way, you were just using our equation in the t equals d over v form, because you automatically calculated from the d equals v times t form that 60 times 2 would be 120 miles. And then you said, okay, 120 miles divided by 120 miles per hour would give you 1 hour. So you probably are pretty good with this equation. You might not even know it, but when we're not accelerating, nobody mentioned anything about accelerating in this problem. You can really use this equation, this d equals v times t, t equals d over v, v equals d over t, and you just can be very confident you're using the right equation. All right, so now if I were to ask people, okay, what was the average speed for that? Okay, so average speed for that trip. A lot of people would say, well, we went 60 miles per hour on the way there, and then we went 120 miles per hour on the way back, and so I just averaged them, it's 90 miles per hour. But I'm telling you, the average speed is not the average of speeds. You can't just average them. That's wrong. Because we went 60 for much longer than we went 120. So we can't just average them. So what I need to do is get the total distance that I traveled, which I think we would agree is 240 miles. And then I would divide that by my total time, which is 3 hours. And I get an average of 80 miles per hour. Right? For that whole thing, if it took me 3 hours, I more averaged 80 because most of the time I was going 60, which 80 is closer to 60 than it is to 120. Right, 90 be smack in the middle. That'd be if I did an even amount of time on both, but I didn't. I did an even distance on both, but not an even amount of time on both. Okay, now average velocity for this problem is kind of tricky because where did we end up? Where we started. So what was our total displacement? 0. So we really averaged for the whole interval 0 for velocity, which seems like a ripoff. All right, so I want to go back to those acceleration equations now. And before I do that, there was one more thing I wanted to clean up from Tuesday, and that is meters per second to kilometers per hour. So I was just thinking, in chemistry, you have to learn this factor label method, so maybe you wanted to see that in the factor label method. So let's say that I started out with 20 meters per second, and I was thinking, okay, I'd like to get that in kilometers per hour, right? Well, the first move I might do is I might say there's 3,600 seconds in an hour, right? Then my next move would be to say, okay, there is 1 kilometer is 1,000 meters. Hopefully this is looking familiar to chemistry, kind of. So now I can start crossing off units. So this has got meters upstairs and meters downstairs, seconds downstairs and seconds upstairs. And you can see that really what I did is I times 20 by 3,600, and then I divided by 1,000. And the only thing that's left is kilometers per hour. Kilometers upstairs, hours downstairs. So 20 times 3,600 divided by 1,000 is 72 kilometers per hour. Right? So the conversion is really to times by 3,600 and divide by 1,000, but I just said a shortcut would be just do 20 times 3.6, 72. All right, so hopefully you can remember that. Okay, got that. So now, a little bit about picking the right equation. So we got 4 equations for accelerations. So here's an important thing to note is, does the question talk about somebody speeding up, slowing down, as we get into the next unit, maybe turning? Does it talk about that? Because if it does, then they're accelerating. If it doesn't talk about that, they're probably going to constant velocity. So the motion worksheet number 1 that you guys have, that's all constant velocity. So there's no need to pick any of these 4 equations. I'm showing you this skill for motion worksheet number 2, which is coming up, because you are going to have to pick the right equation. So you have your 4 equations, and I'm just going to write them over here on the left for safekeeping. You have them on your equation sheet, so you maybe wouldn't need to write them. A lot of people confuse equation 1 and 4. They look similar, but notice that this one, we're adding v initial and v final and dividing by 2. We're really averaging the velocities for number 4. Equation number 1 is finding the change in velocity. In fact, earlier you saw I wrote it like change in velocity over time. So they're not the same, but they look kind of similar, so you don't want to confuse them. Okay, so now you get a problem. Let's say that it says that a car going 70 meters per second, which is pretty fast, slams on the brakes and stops in 40 meters. Find the acceleration. By the way, in this case, it would be considered a deceleration or a negative acceleration. And we're going to talk about what's the difference between a deceleration and a negative acceleration coming up here next week, but not today. What I want to do today is just figure out what equation would I use for this. So I start labeling the stuff that they gave me in the problem. That's my technique. I do it every time. There's really 3 steps that I'd like you to do. One would be, it's often helpful to draw a picture, kind of like I did for going to grandma's house. I'm not going to do that right now because I don't have time, but I would draw a picture. The second step is I would start labeling the things they gave me and the things that I want. And then my third step would be pick the equation and solve with the units. So let's label some stuff. So they gave me a 70, okay? A car going 70, right? So I really have some choices. When I see meters per second, I can identify that's a velocity, but is that an initial velocity, a final velocity? Is our velocity even changing? Well, sure, it's changing. We slammed on the brakes. So we know it's a changing velocity. So it's one of these 4 equations. This is the initial velocity because that's at the very beginning of the problem. So I'm going to call it V initial. VI stands for V initial. Okay. Then it says it stops. Now, most people would blow by that word stops and they wouldn't realize that that's one of my knowns. They would think, oh, shoot, they only gave me 2 things in this problem, 70 and 40. And that's it. Well, no, there's 3. So you don't want to blow by that because we know that you stop. And everybody should know that stopped is a velocity of 0. Okay, and then you got D. D, it doesn't matter if it stands for distance or displacement in this case because you're going one way, nobody turned around, but it's 40. Okay, since it's forward, I'm going to use positive 40. Anything forward is going to be a positive. If you're going backwards, that would be a negative. All right, and then finally, find the acceleration. So I want A. So I just write that down and put a question mark. All right, so now I start looking at my stuff, and I'm thinking, what did we not mention? What are we not looking for? And they didn't give it to me, and it's T. Well, that's the one where we don't know or care about time. It's number 2. So I just write down equation 2. So my next step is write down the equation. Okay. Then I would put the stuff in and kind of check as you put it in that your units are all good. Okay, so this was in meters per second. This is in meters. So that's good. If this had been in kilometers and that was meters per second, that wouldn't work. Or if this was in kilometers per hour and that was in meters, kilometers and meters don't jibe. You don't want to put them in the same problem, nor do you want to have something in hours with something in seconds. So you got to watch your units at this point, just to make sure you don't have to convert something. Okay, and we don't, so that's good. So 0 is equal to 70 squared plus 2a 40. Okay, so didn't bring the calculator, but we'll give it a shot here. So it looks like 70 squared is 4,900, and 2 times 40 is 80. So 4,900 is equal to negative 80a. I just brought the negative 80a to the other side. Right, so then a is equal to 4,900 over negative 80. Right, so looks like that's going to be something really close to 60. Maybe would be like 61 61.125 meters per second squared. Here, we'll double check it with the calculator since I'm bothering to videotape this. First time using the calculator this year. 4,900 divided by negative 80, 61.25. Yes, 61 and an eighth. I mean, and a quarter. So that is a gigantic acceleration, which brings up an important point about acceleration. So I'm not sure if this would kill you, but it's going to be about 6 G's. What is a G? That means the acceleration of gravity. So if you feel your weight, that's like you're feeling the acceleration of gravity. That's 9.8, right? This is 6 times that big. So that would be like 6 G's. So that would be, where you might black out or something like that. So looking at these accelerations, numbers like 60 for accelerations, that's a really big acceleration, right? But we picked the equation by listing our knowns, and then we substituted the stuff into the equation, and we solved. And we were really careful to watch for words like stops. Okay, let's do one more example. I think we have time for one more today. Hopefully you still have your equations, because mine are gone now. All right, so we're going to say that how long does it take to go from rest to 40 meters per second if you travel 160 meters. All right, so I'm going to start listing stuff. So as you're reading, how long does it take to go from rest? Hopefully you don't skip over the word rest, but you know that that's a velocity of 0. To 40, that's a velocity of 40. If you travel a distance of 160. Okay, now this how long, that's time. Okay, so these units are all cool because everything's in meters per second or meters, so we're going to get our time in seconds. All right, so D equals VI plus VF over 2 times T is what I'm going with. Why did I pick that? Because nobody mentioned A. We didn't care about A. We could find it, but nobody cared. So start putting the stuff in. So 0 plus 40 over 2. That looks like we're going to have an average speed of 20 there. That's really what that's doing. Okay, times time, and then that should give me 160. So time is 8 seconds. Right, so we used equation number, did I say number 2? It's equation number 4. Equation 4, because nobody mentioned acceleration. So again, this is the process. You list the stuff, you put a question mark by the one you want, you double check the units, put your numbers in, and then you solve. Right, so you just want to keep using these equations, and we'll just keep practicing. What I'm going to do in the next video is I'm going to talk about graphing, and then I'm going to show you how with graphing we came up with these equations. Right, so you can come up with these equations through algebra, and you can come up with them through graphing and through calculus too. So they didn't just make these equations up, and we'll start looking at that, and that will kind of help you memorize the equations a little more.